mobile app, which is a diet that is supposed to assist mobile diet control. So this is our overview. We'll be going over the background and application of the app, system components. I'll be providing a live video demo, and then code snippets, then challenges that were met during the study, experiment results, related work, and then finally future research. So why study diabetes? Well, diabetes is a very common disease that's prevalent worldwide, where the pancreas is unable to regulate glucose levels, and according to the CDC, there are 37 million cases of diabetes around the world, and many people are pre-diabetic and don't know it yet. So it's very risky. And one of the key factors to keeping a healthy diet is to regulate glucose levels in order to keep diabetes in check. And existing techniques we have to maintain stable blood sugar levels is visiting physicians or doctors for nutritional advice, doing extensive testing in hospitals or clinics, and self-monitoring diet and lifestyle. But these techniques can be really costly, timely, and difficult to implement. So my proposed solution is SmartCarbs, because it is convenient, it's used on a mobile app, and can be pretty much used anywhere, because as long as the user has their phone with them. So these are the system components of the app, and the app basically runs on 5 different components, and it is written in the programming language Dart on Flutter, which is an open source UI development kit. And this app was developed in Android Studio and used to build the Android and iOS versions. And the plugins present in the application components are pubspec, YAML, and which is a metadata file that includes the package name, version, author, and etc. And there are other varieties of plugins, which include TensorFlow, the image gallery, and shared preferences, which are required by the app to function properly. So here, the splash screen, as you can see, is the landing page of the app, and it is one of the most important parts of the basically of the app. And then here's the home screen, which is the second page, which includes the user profile, which users can reset their names and images. And then there's a dashboard right below, which contains bins that store, diet tips and recommendation for future meals. And it also includes through the profile, as you can see, they have the name, username, and then the number of it's the nutritional content they consume each day, and their recommendations. And here, this button with a C, it takes them to the camera view, which they can click on the bottom right of the screen, and it allows them to select their meal type and brings them to this page, this camera view page. And then they can confirm using confirm the food from their clicking. There's like 2 buttons not shown here, like, and then upload images from pictures of the food from their phone, and then confirm it here. Then here's the important part, like the local AI model, which it uses image classification based on image training from the downloaded food, and it predicts the food type and refers back to the food database to retrieve their 5 pieces of nutritional information for each piece of food. And through that, it fetches the type of food from the food database based on the image classification training, and then reveals to the user what type of food there is, and they've uploaded, and the meal results, which is like the total number of calories consumed per day. And there's a meal result page, and there's a home icon, which is not shown in this model here, but it brings the user back to the home page when clicked. So these are like figures of what the app looks like on Android Studios. So figure 1 is the home screen, where, as mentioned, is a profile, and then the name, which you can reset at any time. And these 5 bins, as mentioned before, they add up the total number of calories, carbs, sugar, sodium, cholesterol, 5 important pieces of nutritional advice. They add up the total consumed per day. And once you click on the right camera icon, you're taken to this meal selection page where you select if it's either breakfast, lunch, or dinner. And each of those bins will take you to this page, this camera view page, where this left button, you select images from your mobile device or phone, and this right image, it also like lets you select like the images you want, and then you confirm it with this right check mark icon at the bottom right of the screen. And this is what a typical result looks like for the local AI model. As you can see, bread is like very confident. Like the AI has no trouble in determining that the image is bread. And these are basic nutritional, like the average, calories, sodium, sugar, cholesterol, calories for the piece of bread. And once you confirm the food with the check mark on the right, you can go back and add another food if you'd like on the camera view page. And for example, you add coffee, and then it will appear in bold font and in the meal generation page. Then once you're done adding like all the foods and all the meals for the day, like all the foods you have will appear on this food result page, and at the bottom, the total number of calories will be added up. And there's this home icon page on the bottom right where you can return back to the home screen. Here's like a short demo, video demo, like live demo of the app working. All right, so that was the quick live video demo of the app working on what it would look like on an Android phone. So here are some code snippets that were like essential to the function of the program. So I will explain really quickly what both of them mean. So in the first code snippet, this function here requires the key elements such as static and future data types and allow the application to store data in the to be used in the future. And in this left snippet, static is the keyword in Dart, which allows the data to be accessed freely from other screens without like a direct reference. And this applies to all data within recorded data, which includes like meal type and the names of the food eaten. And static function here in the middle generate food names. It's like creating a food list for each meal and converts it back into strings and records the meal type, either breakfast, lunch, or dinner, and the date of the meal. And recorded data references multiple times within the app since it is static, and it stores the meal type and food type as a data type string, and recorded data basically clears if the meal is like reset or submitted. In other words, the user doesn't press on the check mark icon to confirm the meal. And recorded data is really essential to the application because it is included in other classes such as like meal generation, state class in which like the meal contents are saved. In this right figure, shared preferences is the plugin which allows the application to save a limited amount of and type of information to the phone's or mobile device's memory. And here, the asynchronous and await function saves the meal name into saved preferences, shared preferences before the program moves to the meal result page. And this is asynchronous as the methods don't run in sync with the usual program execution and relies on shared preferences, which may take a lot of processing time. And await before shared preferences is done so that synchronous code has the appropriate data in time when it is running. And otherwise there'd be an error. And the save name variable saves the user's name along with other pieces of information. They entered the list of food names. And not shown in this figure is when the meal is saved from the save name function. So some challenges, major challenges, occurred when trying to develop the model for the AI, which were configuring and fitting the model, figuring out how to save data, and optimizing user experience. So the first challenge was configuring and fitting the model. And it was a challenge because we needed to make a compromise between the accurate predictions and development time spent. And must determine the percentage that the AI is considered sufficiently accurate. In other words, what percent of images it classifies correctly out of 25, for example. And there are privacy concerns over how the images must be collected from the user, because we want to collect the minimum amount of images needed for the AI to function at a desired accuracy without invading the user's privacy. And we must source these images and access them for training, which is something we had to decide. And then finally, we had to consider the robustness of our AI and what it would look like, as well as how many foods it can analyze in regards to development time, and that it can be expandable with new foods in the future. So our second challenge was figuring out how to save the data, because the main concerns are the type, location, and display of the data. So mentioned before, the storage type must be minimum and not invade user privacy. And as regards to data storage, we need to determine whether it must be stored on a back-end server or a phone. And its overall reliability and limitations in storage space. And the method of display must be concerned, because the user has to understand the context presented by the application and how it applies to them, because displayed data can vary from person to person, depending on meal preferences and the foods they entered. So we must make sure they understand the information and it's tailored toward their experience. Third and final challenge was user experience, optimizing user experience so that, as mentioned before, they understand the context of information presented and can easily navigate the app, because common issues app users face are like receiving confusing content, having difficulty navigating the app, and having to fill in data repeatedly if it doesn't save easily, and changing between landscape and portrait mode, for example. So we have to consider method to have the user conveniently access the app's features, such as like the pages and the navigation tools, and ensure the accuracy and consistency of the image classification system. And another issue we faced was that this application requires the user to have several months of continued everyday use at every meal. So, for example, they would need to use this application 3 times a day for 2 weeks, just for optimal results. And then we need to retain user engagement and avoid those navigation issues and confusing content, so that we need to keep users engaged, just because the application requires continual use over a couple of weeks, and that will keep users engaged and minimize the chances of user dissatisfaction or uninstallment of the application. So we conducted an experiment which involved generating 25 images from Flickr Scraper in Google Colab for each of the 10 foods as shown in this bar chart here, and for a total of 250 images. And according to our experiment, apple and bread had among the highest accuracies, while they also had the highest confidence per food type. So here's another bar chart which compares the average accuracy and confidence for each of the 10 types of food. And bread, apple, and lettuce are among the most correctly classified food types by the AI. And this could be because these are very simple foods, and they don't require lots of presentation or preparation. And the Flickr Scraper retrieved clean, easily identifiable images of apple and bread. Whereas compared to ice cream and milk, these two foods are associated with each other as dairy products, and they have very similar colors and can be presented in many different ways. For example, ice cream could be presented in a cup, cone, or different scoops, or in a sundae, and milk can be paired with cereal or other foods, or be by itself. And because of this possible confusion between foods ice cream and milk, they have low accuracies. And also for cooked chicken, for example, the Flickr Scraper only retrieves live images of chickens that were alive, not the dish itself, so that interfered with the AI's ability to correctly classify these foods. Overall, we had 82.4% accuracy and 89.63% average confidence, which is considered quite high. And ice cream and milk had below average accuracies of 44 and 64%, respectively. And in conclusion, the AI responded best to lettuce, apple, and bread because we retrieved easily identifiable images, and these foods, as mentioned before, require little presentation. And these are examples of related works that I looked at in my research. So, for example, this left example is like, it uses KNN, which is like K nearest neighbor algorithm, to recommend meals for diabetic patients, and it sets reminders for them to take their medication and tracks their blood glucose levels, and gives them visual explanation of their diabetic results. And this achieved like 95% overall accuracy. And the middle image is it's a wearable food image classification called DiaWare that displays like the type of food and also classifies it, as well as displaying to the user whether they should or should not consume the food. And it uses simple vector machines and neural networks. In this final example, it's bigger on the right, is another food image classification system, which has gone through nearly 5,000 like food training, like images training, just using k-means clustering and reaching a classification accuracy of 78%. So future research that we would like consider is to expand the food list to include more than 10 foods, like increase the overall accuracy of just of the AI in general, and have the option to add specific serving sizes and do further testing in real world scenarios, because that would help aid our research. So thank you for listening. If you have any questions,